In this lecture, we will discuss the so-called inner product spaces or pre-Hilbert spaces and their corresponding complete versions, the Hilbert spaces. So let us define what is a cisilinear form. So consider a vector space H over the field K. Again, K is either the field of real numbers or the field of complex numbers. A function, okay, denoted by these two parentheses, having two arguments. So it takes two vectors in H, and the value would be in K. So replace this by K. Then this is called a cisilinear form. Okay. On the vector space H, if for any x, y in H and alpha in the field of scalars K, we have the following properties. So the inner product of alpha x, or the value of the form at the vectors alpha x comma y, is the same as alpha times the value of x comma y. So here, if alpha is in the first component, then you could just pull out the alpha. However, in the case of the where the scalar is in the second component, if you want to pull this out, then you should take the conjugate of that scalar. Okay. In the case where the field is the set of real numbers, then you don't need to take the conjugate. The second property is linearity with respect to both arguments. So if you take the value of x plus y comma z, then it's the same as the sum of x, z, and then y, z. And this is the same with respect to the second component. So these two are sometimes called linearity. And this is 2 here is what we call anti-linearity or conjugate linearity. The word here is cisci, which is a Latin that means 1.5. So you can think of this as linear and a half linear. And by that, we mean that it is anti-linear or conjugate linear. So instead of just pulling out the scalar, you need to take the conjugate of the scalar if the scalar appears in the second argument. So therefore, a cisilinear form or cisquilinear form is linear with respect to the first argument, and it is anti-linear with respect to the second argument. And in the case where the field K is the set of real numbers, then instead of a cisquilinear form, we call it a bilinear form. Okay, a quick remark. What would be the value with respect to the form of the zero vector and y? Of course, you could write this as the sum of the two vectors. And then if you apply linearity with respect to the first argument, and here you could see that after cancellation, you get that this is 0. Of course, for all y in the vector space H. And similarly, you could apply the same reasoning to show that the value at y and 0 would be 0. Okay. Now, what is an inner product? Okay. An inner product is a sesquilinear form, so that is symmetric and positive definite. So symmetry means that if I interchange the order, okay, of the arguments, or if I interchange the arguments, I should get the conjugate of that. In the case of real numbers, of course, again, symmetry means that you could interchange the components or the arguments. Positive definite means that the inner product of a vector with itself is always non-negative, and it is zero if and only if the vector is zero. So if you have an inner product, pair it with the vector space H, then we call this pair an inner product or a pre-Hilbert space. Okay. Here the word pre means that, well, in general, this might not be complete. Okay. The complete version will be later called Hilbert spaces. Okay, so pre means it might not be complete. And as usual, we can complete this incomplete inner product space by following the same methods that we have already discussed. We will consider this at the end of the lecture. Two classical examples, of course, the Cartesian product of the field K n times. Okay, so you have this part here. Okay, so the inner product with respect to Kn is just multiplying what the corresponding components, but you need to take the conjugate with respect to y, okay, and then take the sum. Okay. This is in anticipation of getting a norm. Okay. Well, you could see immediately that this is linear with respect to x and antilinear with respect to y. Okay. Well, what you know in complex numbers is that the conjugate of the product is the product of the conjugate. Okay, so that's why in the first property you only have anti-linearity or conjugate linearity with respect to the argument y. And you can extend this into sequences. So recall that L2 is the space of all sequences, say X. So Xk is in let's say the field of scalars. Okay, for all k in the set of natural numbers, having what? That is a square summable. Okay, and an inner product for this is let's say the infinite version of the one given in Kn. Okay. Take note here that what if I take the inner product of a vector in Kn with respect to itself? Of course, I'm telling you already that these are indeed inner products, so you should verify this. So first, prove that it is linear with respect to x, antilinear with respect to y, prove that it is symmetric, and it is also positive definite. So those are left us for you to verify. And you may pause this video for that. Now that you have verified that this is indeed an inner product, so let us look at the case of Kn. What if I would like to take the inner product of x with itself? Then by just simply applying the formula, okay, and the product of a complex number with its conjugate, as you might know, is the square of the magnitude. And this is the Euclidean norm squared. Okay. So in this example, if we have an inner product, then we could generate the Euclidean norm. Okay. And in fact, one could do this in a general setting. So if we have an inner product on H, then this function here. So we define the norm of x to be the square root of the inner product with itself. Okay, this is motivated from this above example here, where you can, of course, take the norm by just taking the square root, okay, both sides. Then this is indeed a norm on H. Okay. Well, one has to be careful here. What do you mean by this square root? Take note that for an inner product, this is always non-negative. Okay. So here we take the principal square root, wherein we take the positive value. Okay. So let us look at the proof of this. So the norm is 0 if and only if, by definition, okay, the square root of the inner product of x with itself is 0. And upon squaring both sides, that means that the inner product of itself is 0. And we know that since we have an inner product, it is positive definite. So this must be 0. So we apply here the fact that the inner product is positive definite. Okay. So the positive definiteness of an inner product implies the definiteness of the function that we would like to show, the function that we would like to prove to be a norm. Next, for homogeneity, okay, so take an alpha, a scalar alpha, and a vector x. What we do here is we just apply the definition. Okay, since we have a square root, I think it's good to look for the square first. Okay. By definition, this is the inner product of alpha x with itself, and applying the linearity, I can pull out the first alpha and pull out the second alpha, but with the conjugate. Okay. Again, a number multiplied by its conjugate is the magnitude squared, and by definition, the inner product of x with itself is just the norm squared. And if you take a square root, you will have the homogeneity. Okay, now to prove the triangle inequality, let us state the Cauchy-Schwarz inequality, which is an extension of probably what you might know in the case of Euclidean spaces. So the absolute value of the inner product is less than the product of the corresponding norms for all xy in H cross H. Okay, so for the moment, accepting this inequality, we can prove the triangle inequality. So let's start with the norm of the sum. We take the square. So this is equal to the inner product of the sum with itself. Okay. Now, if you apply linearity with respect to the arguments, so you have the following terms. Okay. Now, here, by definition, this is norm squared. Well, I'm saying already that this is a norm, but still we're verifying it. But for simplicity, let me call it a norm now. And this is, okay, by symmetry, the inner product of xy conjugate. Okay, so we end up with the following equation. So we have norm squared plus, okay. So if you take the sum of a complex number with its conjugate, you end up with twice of the real part. Okay. And then we estimate the real part by, okay, as we know, any real number is less than its magnitude, and the magnitude, the real number is less than the magnitude of the complex. So we have the following estimate. So this is now less than or equal to norm squared of x plus 2 times the magnitude of the inner product plus the norm y squared. Okay. Now, I will now apply the Cauchy-Schwarz inequality. So the Cauchy-Schwarz inequality here is the following. So here, let me put back the absolute value of the inner product. It is less than or equal to the product of the norms. And now you have a perfect square. So this is the square of the sum of the norms, okay? And if you see from above, after taking square roots, you get the triangle inequality. Okay. So now, let us verify the Cauchy-Schwarz inequality. Okay, so let's prove the Cauchy-Schwarz inequality. To show this, let us consider several cases. First one, the zero case. In other words, the inner product is 0. Then the inequality is trivial. Why? Because if you take, we know that the norm is always, a norm is always non-negative, therefore this is always the case. Okay. Next, we consider the positive case. So what if the inner product is positive? Okay, then the trick here is to consider the following. So we take the inner product of this difference, norm of x times y minus norm of y times x. You take the norm of that vector and then you take the square. Obviously, this is non-negative. Okay, then you apply the definition of the norm. Okay, so you take the inner product of this vector with itself, and then you perform or you apply the properties of an inner product after some calculation. This is equal to the twice the product of the norm squared minus the norm of x, norm of y times the inner product. So you could verify this by simply applying the properties of an inner product and the definition of the norm induced by an inner product. So there is a common factor, which is the norm of x and norm of y. And you end up with this inequality. Take note that neither x nor 0 must be y, because otherwise, if x here is 0 or y is 0, this inner product would be 0, as we have shown at the beginning. Okay. So neither x nor y must be 0, hence the norm must be strictly positive. So I can divide this, and after some manipulation, you end up with the fact that, okay, the inner product is less than or equal to the product of the norms. Since we assume that the inner product is positive, then this must, the left-hand side is the same as the absolute value or the magnitude of the inner product. And then let us now consider the general case. So non-zero case, because we already have shown that it is trivial when the inner product is 0. So here we consider the complex case. Okay. So suppose you have an inner product that is not 0. So the idea here is to convert this in the positive case. So the idea is to introduce an alpha, which is the conjugate of the inner product divided by the magnitude. You can see immediately that here the magnitude of alpha is equal to 1, because the magnitude is preserved or invariant under conjugation. Now we consider the vector z to be alpha times x. And if I take the inner product of z and y, so instead of x, I use alpha x, where alpha is this scalar here. So this is the same as alpha xy, okay, by the first property. And then plugging in the definition of alpha, you end up with this okay equation. This is just plugging the definition of alpha. Now you should recall that if you have a complex number, again, the product of the conjugate and its the product of the complex number and its conjugate is the magnitude squared. So in this, we will get the magnitude of x and y. Okay. Since x and y, since the inner product is non-zero, it has a positive magnitude. So therefore, we apply the second point to this inner product. Okay, we mean this one. So we already know that the Cauchy-Schwarz inequality is valid for the case of a positive inner product. Since the inner product of z and y is positive, then we can apply that one. So now I have here the inner product of z, no, the norm of z, and then the norm of y. Okay, now, since the inner product is positive, this is equal to the inner product of z and y, and this is, if you see in this equation here, this is the same as the magnitude of the inner product of x and y, okay? And how about the magnitude of z? By definition, what is z? Z is equal to alpha x, okay? By homogeneity, this is the magnitude of alpha times the norm of x, but since we know that the magnitude of alpha is equal to 1, so this is equal to the norm of x. So indeed, we have, in this case, that the absolute value of the inner product is what? Less than the product of the norms. Okay. So going back again in the proof, take note that technically we have these two cases. We only need to consider these two cases, okay? The zero case and non-zero case. You can think of the second point as an intermediate step, okay? Since well, if you have a real number and it's positive, it is easier to dwell with these terms. However, the general case or the general non-zero case can be reduced into the positive case as we have seen here. So again, looking back at this theorem, if you have an inner product, you can generate a norm. And as we know previously, if you have a norm, then you can talk about the metric and hence completeness. So in that case, we call a Hilbert space. So a Hilbert space is an inner product space where it it is complete with respect to the metric induced by the norm, and this norm is the one induced by the inner product according to the theorem that we have just presented. Okay, so again, if you have an inner product, you can have a norm. How about the other way around? If I have a norm, is it possible to determine an inner product in such a way that this inner product will, the norm induced by this inner product will coincide with the given norm? Well, that is valid if and only if the parallelogram law is satisfied by the norm. So this is the content of this theorem. So consider a norm space X. Then there is an inner product on X for which this norm is the induced norm, if and only if the sum of the squares of the sum and difference of two vectors is equal to twice the product, twice of the sum of the norm squares. Why is this called the parallelogram law? So in geometry, okay, so let's say this is your X, this is your Y. The diagonal, this diagonal would be X plus Y. The other diagonal would be X minus Y. Okay. So this tells us that if you take the length of the diagonals, the square lengths of the diagonals, take the sum, that is the same as the squares of the lengths of all the sides of the parallelogram. And this is a known fact in geometry. And you could also prove this using vector algebra. So again, if you have a norm on a vector space, you can find an inner product in such a way that that norm is the corresponding or the induced norm, if and only if the norm satisfies the parallelogram law. We will not look at the proof, but those who are interested in the proof, you could look at the course notes. Okay, so as an application, we said that this little LP, okay, space is not an it's a Banach space. So this is a norm space which is complete. However, this is not an inner product space unless P is 2, which we know already, or at least we have mentioned a while ago. Well, to see that this is not indeed an inner product space, we just need to find two vectors wherein the parallelogram law is not satisfied. Okay. So first, let us consider the case where P is equal to infinity. We consider the following vectors. X would be the sequence wherein the first term is 1 and everything else is 0. Y is the same, but we take it to be 1 if and only if we have the second component or second term of the sequence. Okay. And you know that the sum is taken component-wise. And the difference is taken also component-wise. Okay. So if we compute the sup norm of x squared plus the sup norm of x minus y squared, take note that by definition, the sup norm is the largest absolute value. In this case, it's always 1. You square that, you also get 1. So both of these are 1, and hence we have 2. Well, in the case of the right-hand side in the parallelogram law, okay, what would be the norm, the infinity norm, or the sup norm of x? Well, x has components either 1 or 0, so the sup is 1. That is also for y, okay, and we have 4 here. So this means that with these vectors or with these sequences x and y, the parallelogram law is violated. Hence, L infinity is not a Hilbert space. So let's say here, parallelogram law violated by x and y. Okay, hence L infinity is not a Hilbert space. In other words, you cannot find an inner product that will induce the norm of L infinity. Okay. Now for the case where P is finite, we take the same vectors x and y. Okay. So let us compute the P norm squared of the sum plus the P norm of the difference squared. Okay. So the P norm is just the absolute value raised to P. Okay. Raised to 1 over P. But since we take the square, we have 2 over P. And this is the same expression for the difference, because if we take the absolute value, the sign would be immaterial. Okay. And after some algebra, you could show that this is indeed, or at least this is equal to 2 raised to 2 over P plus 1. With respect to the right-hand side in the parallelogram law, P squared okay, so we will have twice of, since we only have one term, we will have 1 over 2 raised to P. The rest would be 0. And this is the same for the norm of YP. Well, this is 4. Note that this quantity here is equal to 4. Okay, if and only if, well, the power of 2 would be equal to 2. So let's write it here. These two are equal. if and only if 2 over p plus 1 is equal to 2 or 2 over p is equal to 1. And this is true if and only if p is equal to 2. Put in another way, so if p is not equal to 2, then these two quantities on this part here are not equal. Again, you can see here that we have vectors violating the parallelogram law. And from this, we therefore conclude that LP is not a Hilbert space when P is not equal to 2. Of course, P here is between 1 and infinity. So there, we have Banach spaces that are not Hilbert spaces. So to close the section on Hilbert spaces, let us state this theorem, which is in the same spirit as what we have already mentioned in the case of metric spaces and norm spaces. So if you have an inner product space X, you can find a Hilbert space, let's say X bar, and a map from that Hilbert space into X bar, call it J, and this map is linear. So let us put here. So a linear map J, wherein it is, let's say, inner product preserving. Okay, and this will also imply that it is norm, hence it will be also distance preserving, hence an isometry. And again, the image of this map is dense in the Hilbert space. So again, identifying J of X by X, we can say that an inner product space that it is not necessarily complete can be embedded densely in a complete inner product space or a Hilbert space. Again, we will not prove this, but as you might know already, you follow the same equivalence relation, and the inner product, let's say, that you would like to define. So consider equivalence classes of Cauchy sequences. You take the inner product of the complete Hilbert space by taking the limit of the inner products corresponding to the representatives. Okay. And that's the idea of the proof. Again, following the methodologies in the proof provided for metric spaces, one can show this. Okay, so let us summarize the discussion in this chapter. So the past few discussions, we've started from the largest spaces that we are interested in downwards to the smallest. So first, we have the topological spaces, where you have here again the notion of open sets. And hence, you will have the concept of convergence, continuity, and compactness. With this, you have the metric spaces, generalizing our notion of distance. And we know that a metric will induce a topology called the metric topology. for obvious reasons. And in this way, the open sets are generated by the open balls, okay, with respect to the metric. Going inside, we have the norm spaces, which is a generalization of length. So norms are generalization of lengths, and as you can see, the metric generated by norms are translation invariants. So once you have a concept of a length, you can have a concept of a distance. So the distance between 2 points would be the norm of the difference. Okay, so a norm induces a distance. And finally, we have the inner product spaces, although we have not defined here yet the concept of angles, but an inner product induces a norm, and that is simply by taking the square root of the inner product of the vector with itself. Okay. And the complete versions for norm spaces, you have the Banach spaces, and for inner product spaces, you have the Hilbert spaces. And that's it for abstract spaces. In the next lecture, we will consider more concrete function spaces. So see you there.